So today I will present you a high-level view of a volumetric video. So I am working at InterDigital, and we just recently joined 5G MAG, so we are happy about that. And we would like to open our platform that we have developed and also in collaboration with Philips. So the goal today is to give a high-level view of the standards and the standards and where we are in the implementation. So I will give a first view of what is volumetric video. So in fact, there are different scenes that can be captured with different setups, different rigs, and it will lead to different approaches for the codecs. So here, what you see on the top is a studio with a green screen from our partner XD Production, and they have cameras all around in these setups, 60 cameras in fact. And what they capture is the scene that is in the middle with all angles, and this will generate a volumetric video where the end user can navigate dynamically into the scene from all sides. On the bottom of the bottom figures, it's a different setups where the camera rigs here is a linear rigs. So you see the cameras. So it's a setups that is provided by Philips. And with this kind of setups, you capture a different scene where you have also the backgrounds, and you have all the textures from the backgrounds to the foregrounds. So this will lead to a different type of scene where the movement, the dynamic movement into the scene is enabled and depends on the size of the capture of the rig. But in the end, you also get different information on the background. So here is example of this kind of resulting video. Is on the bottom left here you have a video, and you can turn around the person from the end user devices. And if I move on to the format, this one is called dynamic point cloud. So in fact, each frame is represented by a list of points, which are points in the 3D space without relation between them. And each point has a position, a geometry, and attributes. So the attributes can be a texture, transparency, and then they evolve in times. On the right, it's a multi-view plus depth. So in this representation, the input is multiple views. So this is the output of the different cameras. And then the depth information of each pixels has been computed. Either it can be directly computed if the images comes from, for example, computer-generated graphics. And then the depth information are quasi-perfect. But in the general case where we want volumetric video of natural contents, these depth information are estimated with techniques like photogrammetry or others, and they are outside of the standards, and they can lead to some errors in spatial and temporal artifacts. So now I will link this introduction of two types of scene of volumetric video with the MPEG V3C standards. So in MPEG, several specifications have been defined to cover this type of video. So the first one, V3C, which stands for Visual Volumetric Video-Based Coding, is a standard that will define the bit stream, how the data are aggregated into unit, and that can be then merged to form a V3C bit stream. And inside this V3C bit stream, you can have encoded video according to these codecs. So VPCC. VPCC is a video-based point cloud compression. So it's a codec that can take as an input a point cloud that's the socket that we just previously see. So this standard is published and is available now. The second one is MPEG Immersive Video. So it's also a standard that is published, and it takes as an input multi-view plus depth video. It can also support another format, which is called multi-plane image. Maybe I will talk about it later. And there is a third format, video-based dynamic mesh coding for dynamic mesh input that is being currently developed. Then once you have this V3C bit stream, it enables to compress your volumetric video, either for storage or transmission. And in MPEG, there has been a specification of carriage of V3C, which specify how to transport this data, either for file like ISO-BMFF or for MPEG- streaming. Also in this scope is the scene description standard that describe how to compose a scene with different assets like 3D object, media components. And they can compose a scene with 2D or volumetric video or future media like haptic. So a bit more into the technical detail of the approach taken in MPEG for this codecs. So the approach that has been taken is to leverage the 2D video encoder. So what you see in the figure here is on the top, you have the different format, like a volumetric video. It's a general term, but in fact, it's point cloud video or multiple plus depth or multiplane. And these are the input of the specific encoders. And the first step is to do a 3D processing to extract from this input format one or multiple video stream, and first a texture video, and then it can add, depending on the format, transparency information or geometry or occupancy, plus metadata describing these streams. Then once you have generated these 2D video streams, you can leverage the existing 2D video codec. So it can be HEVC, VVC, or future video codec. And this is where you have the gain of the compression. And as a result, you have a V3C bit stream that aggregates these different videos. And on the receiver side, it's the opposite. You will use 2D video decoder, so existing hardware video decoder to decode the video streams. And then you have a 3D reconstruction step in CPU or GPU to reconstruct the volumetric video. And then on your end device, you can render and generate the final view that is requested by the application. So I have here an example applied to VPCC encoder. So on the top left, you have the point cloud. So it's here it's a one frame. So the idea is to project on the surface of a cubicle this point cloud. You then get 2D images, and then there is a process of aggregating these images and the patches to have all the information aggregated in one frame. So you get here in the middle a texture frame, and you also generate the geometry information, occupancy map image generation. This will give you the 3 video streams that can be encoded with video encoders. And although they don't look like classical 2D videos, the encoder are perform well to compress this video. Then this 3 video stream plus the metadata are multiplexed to form the V3C bit stream. So on the receiver side, it's the inverse process where you demultiplex. You have your video strings that you decode with 2D video decoder. And then from this video, we reconstruct the 3D volumetric video. So now I move on to MIV. So it follows the same path. So in this example here, we have as an input 16 views. it's a 4x4 rigs. So it can be multiple view and devs, or it can be converted into multi-plane images. And in the input of the MIV encoder, it will follow the same path as VPCC. It will generate one video texture that aggregates the information from a main view plus additional patches. And then you can have a geometry or transparency video to form the V3C bitstream. And same for the decoding and rendering. Interesting also is that on the receiver side for MIV, what you get is a volumetric video. So it means that the output of the decoder is not the original views. It's actually a volumetric video where you have all the intermediate views. And then if you want to do, and then you can move in this viewing space. You can navigate between the views, but also between this intermediate space. If you want to have a comparison like we do for a classical 2D encoder, you can extract from this viewing space the original views and then compare the quality of the encoding. So now I will move on to the platform, which is my third and last part of the presentation. So this is an implementation that we have done in collaboration with Philips. And we focused more on the rendering side. So for the capturing, we work with partner or with content that we generated ourselves. Then we use the tools for MPEG for encoding and segmenting. And then what I present here is more the implementation on the rendering devices. Today we have an implementation that is available, and we can share with partners for evaluation. But of course, the goal to present here is that we would like to open this platform in 5G Mag and see the interest. So maybe we can discuss that later. But this would be the goal. So today, the platform, we have a dash packager. So once you have the input content and encoded the data with MPEG encoders, we have a dash packager which is a tool that will take as an input the V3C bitstream, and the output, the data will be segmented and encapsulated as dash segments. Therefore, it enables the streaming over existing networks, CDN network or wireless networks. And on the receiver side, we have an implementation with one native decoder plugin, which handles basically what I described previously, the demuxing, addressing the 2D video decoder and synthesizing the 3D reconstruction of the video. And host application that is a Unity application that can enable to do some test, interoperability, or more illustrate use cases for demos. So today, the implementation works on a Windows laptop, Android and device, like smartphone and tablets. And just recently, we also have implemented it on the Meta Quest 3. So it's working well. So for Meta Quest, the difference is that we will, from the volumetric video, we will extract two views in order to have the stereoscopic view and real 3D rendering. And just a bit more detail on this implementation. So the native decoder plugin can take as an input either local data, a V3C bitstream, or dash segments. Then it will demux the data to address the video decoder. And then together with the metadata, this is sent to a synthesizer, which is the 3D reconstruction in a GPU or CPU. And there is one synthesizer per codec. So one for VPCC, one for multiple view plus def, one for MPI, and we could imagine to have new synthesizer coming. And for the application, basically, you retraced content to be decoded. And then from the application, you select the viewing angle with the viewport and camera information so that the plugin gives back and renders the appropriate views of the video of the scene. Okay. I have also some evaluation results that we performed last year, and it gives you also some example of the content that we have. So here you see a demo that we have presented last year, and on the tablet you see that it illustrates how you can navigate into the scene, into the video, moving, changing the angles. So the video, in fact, is a soccer guy, and you can change the virtual background. Here it's a 3D background. When it's black, it's removed. So here you see only the volumetric video. And here it's another example where the volumetric video is inserted in an augmented reality environment, so using the camera of the tablet. This video has been captured with 60 cameras, 4K cameras, and for that, with a partner XD Production that generated the dynamic point cloud. This is another example with a capture where you see the studio and there are two characters into the same video. We skip this one. So you have here some details on the test contents. So we have input point clouds, and then you have the compression ratio that varies depending on the content. And you can have, you see that the output bit rates, for example, varies from a couple of megabits to 20, 27, 30 megabits, depending on the number of points and the quality. And here it's an illustration of the MIV setup where you capture, you have here more off-the-shelf cameras, and it's provided by Philips, and they've captured soccer tricks here. So what you see here on the video is a 2D video captured with a professional camera. And now here it's MIV stream. So again, the end user from its application can change its point of view dynamically, and it's done locally on the end user device. So this stream is captured with 8 cameras, and the depths have been estimated from these 8 views. This is another example where so this is a 2D video from a professional camera, and the MIV volumetric video captured with 6 Azure Kinect camera. And again, the depth has been estimated from the 6 cameras. And you see that you can change your point of view dynamically into the video. And lastly, content generated with MPI. So here it's 2 really different content. On the top left, it's CGI content, so it's generated with Unity. So in this content, it was to show that, in fact, we can have really good estimation of the depth. So with this content, we achieve really high compression ratio because we don't have artifact on the depth estimation. And the one on the right with the ladder is a really complex content on the opposite, where you have a lot of details, a lot of objects in the front and backgrounds, and it's much more complicated to estimate the depth estimation, and then it leads to a temporal artifact that will reduce the efficiency of the compression, but it's not due to the codec, it's more due to the depth estimation. And these are the final evaluation results that we have performed on Windows laptop and Android smartphones. And in fact, for all these contents, for point cloud, we achieved the targeted FPS. And for MIV, so the targeted FPS is achieved on the Windows platform. And for Android, we are close to the target. And the two that are difficult are the one with where we have some issue on the depth estimation. And since then, we have also improved our application that we think that it will be achievable soon to have the target FPS. So as a conclusion, what I presented here is a first implementation of MPEG V3C standard, where we have one plugin and one application. We also have implemented the streaming stack with Dash. So it gives an insight of the feasibility, the maturity of this codecs, and also that it can be integrated into the XR ecosystem with platforms such as Unity. We have also I'll not mention in this talk, but we are also working with Broadpeak. We have a collaboration, and we have a joint demo at MWC, where we validated the Dash streaming over their CDN networks. So they have the Dash packager on their origin server, and then we stream over their CDN the V3C bitstream and receive them on the end devices. And we use open standards like MPEG to demonstrate that the compression efficiency of MPEG video codec to DVD codec are leveraged. So today, the results that we showed is for HEVC compression. But of course, if the VVC is deployed into the end device, this V3C codec will benefit from the stronger compression efficiency. And also, so this V3C format are now open to be integrated in other standards like scene description for more complex scene composition on to other use cases. So this will end my presentation.